So we learned back in section 5 or 1.5 about how we can transform graphs by shifting, stretching, shrinking, in various aspects of that. So the important part to remember when you come in with dealing with absolute value functions is this is the general form of an absolute value function, and where all these are true. The part that people make mistakes with is the left-right shifts. These are the opposite, because what you're doing is the general form is x minus the number, and if you're going left to -2, say, that's going to become +2, x plus 2. Okay, so what do you mean? What do I mean by going left to right? Well, what you got to remember is that the coordinates of the vertex of these absolute value functions is always the x is the h, the y is the k. Okay, so you just gotta keep that in mind as you're working with this. And then this is sort of like the slope. You gotta look at how fast is rising, falling, that kind of thing. So here's that example 3 from the textbook. To kind of walk you through that, I know that normal everyday absolute value graph looks like that, right? With a vertex at 0, 0. So what I'm seeing that vertex slid to the right 3 and then down 2. So the coordinates of that vertex are 3, -2. And I write -3. Okay, so I know that inside the absolute value bars, I'm going to write x minus 3 because it's going right 3. And then outside it, I'm going to put the -2. Now the only thing I have to worry about is any stretching that's going on. So what I'm seeing here, normal everyday absolute value graphs have a slope of 1 or a -1 if you're coming down from the left. And so for this one, I'm going up 2 over 1, up 2 over 1, and I'm going down 2 over 1. So this slope, so to speak, is a 2. And that would be the equation of that absolute value graph. Okay, and that's exactly the process I use to figure these out. I find the vertex, write that in, and I have to decide on what the rise and the run, what's the slope, so I know whether there's some stretch or shrink going on. And the other thing that this example doesn't do is if it's reflected around the x-axis, you have to make this negative. So this would become -2 if it were reflected. Okay, so hope that helps. Okay, so here's the first question out of the 2.5 homework and out of the textbook, and you ought to try to work this yourself and try to decide. You can either look the answer up in the back of the book, or you can come back and finish watching this video. So what I'm noticing is that this graph the vertex has been shifted left 2, up 1. So I'm going to take my absolute value graph, and I'm going to write x plus 2, because you've got to remember this is a times the absolute value of x minus h plus k. And if I've got a coordinate for a vertex of -2, +1, that negative turns to positive. That's why I wrote if it goes left, it's plus inside. And this graph is shifted up 1, so I'm going to put the 1 as k. And then I get to decide on if there's a shrink or a stretch going on. And what I'm seeing is this going up 1 over 2. So that tells me the stretch, or shrink in this case actually, is 1/2. So f of x or y equals that absolute value graph. And that we could certainly check it, and it would work. Again, this is problem number 3 from that 2.5 homework. Okay, so to do it, remember I'm going to write y equals a times the absolute value of h, x minus h plus k, and I see the vertex of this has been shifted right 3, up 3. So I'm going to do absolute value of x minus 3, up 3, and then I'm seeing that it's open down, so I know a is going to be negative because it's been reflected down, and I'm seeing it's going down 3 over 1, so it has a stretch of 3, and that's that inequality. Look at all those 3's. Okay, I mean, this absolute value graph.